Hey there, future pilots. Today we're diving into the fascinating world of airfoils. You might know them as those big spinning blades on top of a helicopter. But there's a lot more to airfoils than meets the eye. They're the key to unlocking the magic of flight, and understanding them is crucial for any aspiring helicopter pilot. In this lesson, we'll break down exactly what airfoils are and how they work. We'll explore their shape, size, and the different forces that act on them. Get ready for a wild ride through the fundamentals of helicopter aerodynamics. So, what exactly an airfoil? Think of it like this. An airfoil is any surface designed to produce lift when it moves through the air. In a helicopter, the rotor blades are the airfoils. Just like the wings of an airplane, they generate the upward force needed to overcome gravity and keep the helicopter in the air. What makes an airfoil special is its unique shape. It's usually curved on the top and flatter on the bottom. This shape is crucial because it's what allows air to flow over and under the airfoil in a way that creates lift. To truly understand how airfoils work, we need to delve into the intricate details of their structure and function. We need to break them down into their key parts, each of which plays a crucial role in the overall performance of the airfoil. Let's imagine looking at a helicopter blade from the side as if it's frozen in time. This perspective allows us to clearly identify and understand each component. Blade span. This is the distance from the tip of one rotor blade to the tip of the opposite blade. Think of it like the wingspan of an airplane. The blade span is critical because it determines the area over which lift is generated. Chord line. This imaginary line runs from the very front leading edge to the very back trailing edge of the airfoil. The chord line is essential for defining the shape and aerodynamic properties of the blade. Chord. This is the length of the chord line and represents the width of the airfoil at any given point. The chord length can vary along the span of the blade, affecting the lift distribution. Mean camber line. Imagine drawing a line halfway between the top and bottom surfaces of the airfoil. That's the mean camber line. This line indicates the curvature of the airfoil, which influences the lift and drag characteristics. Leading edge. This is the rounded front edge of the airfoil, the part that first meets the oncoming air. The shape of the leading edge is crucial for minimizing drag and ensuring smooth airflow over the blade. Trailing edge. This is the sharp, often pointed back edge of the airfoil. The trailing edge helps in controlling the airflow separation and reducing turbulence behind the blade. Resultant relative wind. This is the direction the air flows over the airfoil. It's a combination of the air the helicopter is moving through and the air being moved by the spinning blades. Understanding this concept is vital for analyzing the aerodynamic forces acting on the blade. Induced flow. This is the downward flow of air created by the rotor blades as they spin and generate lift. Induced flow is a key factor in the overall efficiency and performance of the helicopter. Understanding these key terms will help you grasp the finer points of airfoil dynamics and how they relate to helicopter flight. Each part of the airfoil has a specific function that contributes to the lift, stability, and control of the helicopter. By mastering these concepts, you can better appreciate the complexity and elegance of helicopter design and operation. Not all airfoils are created equal. Each airfoil is meticulously designed to serve a specific purpose, and their differences can be quite fascinating. They come in different shapes depending on their purpose. Some are designed for speed, others for stability, and some for maximum lift. The two main types are symmetrical and non-symmetrical airfoils. Each has its own unique characteristics and applications. Symmetrical airfoils. These airfoils, as their name suggests, are the same shape on the top and bottom. This symmetry allows for consistent performance in both upright and inverted flight. Picture a perfectly symmetrical leaf. Just like this leaf, symmetrical airfoils are balanced and stable. They produce lift but are mainly used in applications where stable flight at various angles is crucial, like helicopter tail rotors. This stability is essential for maintaining control in diverse flight conditions. Non-symmetrical airfoils. These airfoils are more common and are the workhorses of lift generation. They are designed to maximize efficiency and performance. They have a curved upper surface and a flatter lower surface. This design helps in creating a pressure difference that generates lift. This asymmetry is what makes them so effective at producing lift, making them ideal for a helicopter's main rotor blades. The main rotor blades are crucial for the helicopter's ability to take off, hover, and maneuver. The shape of the airfoil dictates how the air flows around it, directly influencing the amount of lift it can produce. Understanding these shapes is key to mastering the principles of flight and improving aircraft performance. Now let's talk about lift, the force that makes helicopters defy gravity. How do airfoils actually generate this upward force? It all boils down to pressure differences. Remember the curved upper surface of a non-symmetrical airfoil? As air flows over this curved surface, it speeds up. Faster moving air creates lower pressure. Meanwhile, the air flowing under the flatter bottom surface moves slower, creating higher pressure. This difference in pressure between the top and bottom surfaces results in an upward force, lift. The greater the difference in pressure, the more lift is generated. And that, my friends, is how helicopters take to the skies. Section 6. Blade span and chord size matters for lift. We know that the shape of an airfoil is crucial for lift, but size also plays a significant role. Two key factors are blade span and chord. Blade span. As we learned earlier, this is the distance between the tips of the rotor blades. A larger blade span means a larger surface area for air to flow over, resulting in greater lift. Think of it like having bigger wings on an airplane. Chord. This is the width of the airfoil. A wider chord generally means more lift, as there's a larger surface area for pressure differences to act upon. Helicopter designers carefully consider blade span and chord when designing rotor blades to ensure they generate enough lift to carry the helicopter and its payload. Section 7. The twist in the tail. How blade twist improves performance. If you look closely at a helicopter's rotor blades, you'll notice they're not perfectly flat. Instead, they have a subtle but crucial design feature known as blade twist. This twist means that the angle of the airfoil changes along the length of the blade. The twist is more pronounced at the tips and less so near the hub. This is called blade twist. But why is this twist so important for helicopter performance? It all comes down to maintaining even lift distribution across the entire rotor disc, the circular area swept by the rotating blades. This is crucial for stable and efficient flight. As the blades spin, the tips move much faster than the sections closer to the hub. This difference in speed can create significant aerodynamic challenges. Without blade twist, the faster-moving tips would generate significantly more lift than the slower-moving inner sections, leading to instability and control issues. This imbalance could make the helicopter difficult to control and less efficient. Blade twist compensates for this difference in speed by reducing the angle of attack, the angle at which the airfoil meets the oncoming air, at the tips. This reduction helps to balance the lift generated along the blade. At the same time, the angle of attack is increased near the hub, where the blades move slower. This increase ensures that the inner sections of the blades also contribute effectively to the overall lift. By carefully designing the twist, engineers can ensure that the lift is more evenly distributed across the entire rotor disc. This even distribution is key to achieving a balanced and stable flight. This ensures a more even distribution of lift across the entire rotor disc, resulting in smoother, more stable flight. The helicopter can then perform more efficiently, with better control and less wear on the components. So, the next time you see a helicopter in flight, remember that the twist in its blades is a marvel of engineering that plays a crucial role in its performance and stability. Section 8. From Theory to Practice. Seeing airfoils in action. Now that we've covered the theory, let's see airfoils in action. Imagine you're observing a helicopter taking off. As the pilot increases the engine power, the rotor blades spin faster, increasing the speed of the airflow over the airfoils. This creates a greater pressure difference between the upper and lower surfaces of the blades, generating more lift. When the lift force exceeds the force of gravity pulling the helicopter down, it lifts off the ground. Understanding how airfoils work is not just about memorizing terms, it's about seeing the principles of lift, drag, and airfoil design come to life in the real world. Section 9. Mastering the Skies, the Importance of Understanding Airfoils. As aspiring helicopter pilots, understanding airfoils and their role in flight is not optional, it's essential. It's the foundation upon which all other aspects of helicopter aerodynamics are built. By grasping the concepts of lift, pressure differences, airfoil shapes, and blade twist, you'll be well on your way to becoming a skilled and confident pilot. So, study hard, ask questions, and never stop exploring the fascinating world of airfoils. The sky's the limit.